All right, guys, these problems that we're going to talk about coming up here in this chapter is all about retrosynthetic analysis. And so one of the hard things about organic chemistry is coming up with a solution for a synthesis problem, coming up with a pathway from a reactant to a product, or from any reactant to a product. In these questions, we're going to give you a reactant, but in some questions, you don't even get reactants. It just says pick something. And there might be some rules around what you need to pick, and you kind of have to fall within those rules. But at the end of the day, this is a pretty significant challenge for most students. And so there's a couple of things that you should do as far as suggestions are concerned in order to tackle these problems. Now, if you're really, really good and you know every single reaction backwards and forwards, then you might look at a synthesis problem like this and say to yourself, oh, here are the reactions. That's very few, that's very few students that can do that. And so what we do is we say, okay, how do we break this down? How do we come up with a set of suggestions on how to approach these problems so that you can solve them a little bit, so they can become a little bit more tractable for someone who may not be quite at that level. And so we're going to start with some of these things. The general idea of retrosynthetic analysis is to start with the product and to think backwards. What I tell my students sometimes is that you kind of just have to trust in the method. So at the end of the day, if you ignore the reactant and you just kind of work backwards from the product, and you just hope that eventually that you're going to get there, you're going to get to the reactant. And that generally you do. And if you don't, then maybe just start over and try some other reactions. But it's really hard to do that on faith. And so it really is best to then use a combination of working backwards, but also keeping in mind where you're going, or where you're starting as far as the reactant is concerned. There's some other things to think about as well. And generally, what are the functional group transformations? How many carbons are there? If you're not counting carbons, you're not doing it right. That's one thing I like to say. And what do you see, and what reactions provide you with what you see? So let's take this one for example. What do we see? What do we see in the product? Well, we see an alkane with a halogen on it, a haloalkane. The alkane is in a position at the end of the molecule. Now, I said let's count carbons. So we've got 1, 2, 3, 4, 5, 6. And in the reactant, we have 1, 2, 3, 4, 5, 6. So one thing we know is that we don't have to add or remove carbons. So that means all we need to think about are functional group transformations. Okay, well, how do I get a bromine in this position? This is a primary position. And the other one here, the next closest one, is a secondary position. So we do know how to add bromine to something. Bromination or hydrohalogenation is the reaction. But we need to add it in a specific place, and that place is at the more substituted position, or excuse me, in this case, it's the least substituted position. So I know that I can add a bromine to a molecule like this in an anti-Markovnikov fashion if I do HBr in the presence of peroxide. Okay, well, let's continue to go backwards. Well, how can I make a molecule like this? Well, this is an alkane, or excuse me, this is an alkene. And I don't know very many ways to make alkenes except for elimination reactions. And so if I were to think about an elimination reaction, I would want to have eliminated something from here, or I could have eliminated something from there. Now, let's just think a second about the yellow location. If we're going to eliminate a leaving group from that location, then this is a situation where we're going backwards. We're going in a circle. And so considerations that lead you in a circle are usually not the way to go, right? And so this is telling me when I'm looking at the red location or the yellow location, I'm going to think about the red location because I just came from a structure that had a leaving group at the yellow location. So I don't want to go around in circles. And so let's just think about that red location. Well, I could have a bromine or another leaving group in that location. And then I could create a double bond there if I make the Hoffman product. And so I'd have to use something like T-butoxide. Okay, can I get this bromine? Where can I get this bromine? Well, I'm in the same, I'm sort of thinking about the same thing happening, right? How do I get a bromine on a molecule? Well, I can do hydrohalogenation. Okay, well, is it at, where was the double bond then? What was the double bond here? Well, this is just the same situation I was telling you about before. This is going backwards in a circle, and you want to avoid that one. So that's not where we're going to think about the double bond being. We're going to think about the double bond having been there. Okay, well, if the double bond was there, then was this a Markovnikov or anti-Markovnikov addition of the bromine? Well, this was an anti-Markovnikov addition of the bromine. So that means that, oh, and look, well, if the double bond was there, then I'm right back to my reactant. I've completed the path. And so this one is still HBr-ROOR, the same as the first, well, the same as the last step. And so now I have my synthesis solution. Step 1, HBr-ROOR. Step 2, T-butoxide. And step 3, another anti-Markovnikov hydrohalogenation. Okay, that's the solution.